Up to this point in our discussion of the unit circle, we should be pretty comfortable with using degrees, getting the reference angles in quadrant 1 and then extending that out to the other 4 quadrants and finding the exact value of all the trig ratios, sine, cosine, and tangent for basically any angle on a unit circle. But that's just part of the story. There's two other important things. Well, there's three other important things, and we're going to talk about one of them here, and that is that there's not just 3 trigonometric ratios, sine, cosine, and tangent. There are 6, and the other 3 are what we're going to talk about in this video. So, recap: sine, cosine, and tangent are the ratios that discuss the sides of a right triangle, and there's also these other 3, and they are cosecant, secant, and cotangent. And whereas sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. It's the flip of that. Okay, it's the reciprocal of that. Cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. Tangent, opposite over adjacent, cotangent, adjacent over opposite. So if I wanted to use this triangle down here, in a previous video we learned that would be the square root of 41. We get that using the Pythagorean theorem, a squared plus b squared equals c squared. And so if we have these 3 trig ratios, well then what would that mean in terms of cosecant, secant, cotangent? Recall that sine of this would be opposite over hypotenuse, so 4 over the square root of 41 rationalized would be 4 root 41 over 4. Over 41. Cosine is adjacent over hypotenuse. It's going to end up being 5 root 41 over 41. Tangent was just the opposite over adjacent, so it was just 4/5. Well, if you think about it, all that we would be doing for cosecant, secant, and tangent would be flipping these results. So we'd be flipping these ratios, really, okay? And so the easiest one to do, if we have tangent is just 4/5, cotangent is just going to be 5/4, and it's adjacent over opposite, right? Adjacent over opposite. So that works out fine. Now, how do we deal with cosecant and secant? Well, same way. We can say that it is the hypotenuse, right, divided by the opposite. So for cosecant, the square root of 41. Square root of 41 over 4. Notice this was the first thing we wrote for sine. And if we flip that, we get this. Okay, we get this. Then secant is the flipped version of cosine, and so the reciprocal of cosine. So if cosine was, cosine is adjacent. So cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So it would be the square root of 41. Square root of 41 over 5. And so in some ways here, it's actually a little bit more convenient for us to say what the cosecant, secant, and cotangent are. Let's explore that idea a little bit more here. So these are the 3 reciprocal trig functions. That's what they're called, the reciprocal trig functions. And if we think about this in terms of just sine and cosine, right? If cosecant, let me redo that. If sine of theta is equal to the hypotenuse, I'm just going to say h over o, okay? O over h, so O over h. Well, then the reciprocal is cosecant. Couldn't I then just say that cosecant of theta is equal to 1 divided by the sine of theta? That's the same thing, okay? It's like if we flip this, if we flip these two things, if we put 1 over sine and we have to flip these two things and we get cosecant. Okay, secant, by the same reasoning, cosine, remember, is adjacent over hypotenuse. So that means the reciprocal of cosine is secant. So here's secant is the reciprocal of cosine. Okay, same thing for tangent. Tangent is opposite over adjacent. Tangent of theta is equal to opposite over adjacent. So by that same reasoning as before, the cotangent of theta is equal to 1 divided by the tangent of theta. And if you're looking at this and you're thinking to yourself, why on earth is this necessary? That is a completely valid question, because in order to know cosecant, secant, or tangent, you need to by necessity also have the same information that you need to know to get sine, cosine, and tangent. And it turns out that there will never be a problem in analytic trigonometry where it requires the use of sine, cosine, or tangent, it requires the use of cosecant, secant, or cotangent to solve a problem, because we will always have sine, cosine, and tangent anyway. And so then that begs the question, like, why do we need them? Well, I can think of two reasons. Okay, one of the reasons is that it will be occasionally. In fact, in the previous example, we saw that we had that the sine of theta in the previous example was 4 divided by the square root of 41. Well, this requires a rationalization step here. And so we'd have to go and do square root of 41 over square root of 41, and then we have 4 root 41 over 41. Well, it would be easier just to write the cosecant of theta being the square root of 41 over 4. That's already rationalized. Now, this value, cosecant of theta, might not be as useful for us, but if it was a matter of multiplying out different things, then we can avoid nasty division problems. So these reciprocal trig functions, being able to flip a ratio essentially, can really save us some time and some headaches when it comes to just doing some basic arithmetic things like multiplication and division. So if we can avoid a whole division step by using a reciprocal trig function instead of a trig function, that's pretty great. And you'll see that that actually does come into play when you talk about analytic trigonometry. Depending on what sides of triangles you're given, it can be really helpful to use the reciprocal trig functions. Never necessary, but potentially helpful. The other reason that these can be helpful is in calculus. So it's not applicable to this class, but there are certain there's things in calculus called derivatives, and there's derivatives of certain trig functions that are just so much nicer to work with than other ones. And so we can essentially substitute things in here to like help us evaluate things or take derivatives of things and do things in calculus. Okay, so we also need to talk about reciprocal trig functions in the unit circle. Okay, so if we just remember, this is like unit circle. To this point here, we'll call it x comma y, and this radius is 1. That means that this length in the x direction, like that length there, that's x, and this vertical length, that's y. And so we know that sine of theta, sine of this theta, is just going to be the y value because it's y divided by the radius in this case being 1. Cosine of theta is x, so x divided by 1. Tangent of theta is y divided by x. And so then it would make sense to us, hopefully, that the cosecant of theta, which is the reciprocal of sine, is 1 over y. The secant of theta would be 1 over x, and the cotangent of theta would be x divided by y. And so that's really it. If you're asked to like evaluate certain things, and we can do that pretty easily. So when it comes to actually finding like the values of reciprocal trig functions on the unit circle, a completely valid way of doing this would be to first find the sine, cosine, and tangent of a given angle, and then flip what you get. So really quickly, the sine of the sine of 30 degrees is 1/2. And so if you flip 1/2, you get 2, right? Because cosecant is 1 over sine. Same thing for cosine. Cosine of 30 degrees is root 3 over 2. If you flip that and you rationalize, you get 2 root 3 over 3. The tangent of a 30-degree angle is the square root of 3 over 3. And if you flip that, you'll actually get the square root of 3. Okay, so moving on then, sine of 45 degrees, and we don't have to do all of these, but the square root of 2 over 2 is the sine of 45 degrees. It's also the cosine of 45 degrees. If we flip that, we'll just end up with the square root of 2. Because by the same exact reason why tangent and cotangent becomes the square root of 3. And then secant is also the square root of 2. Tangent of 45 degrees is 1, so 1 over 1 is 1. Okay, and so it just kind of goes on and on like this. We could do the rest of these too, but why bother? What's important is that we recognize that there are certain, because these are denominators, right? We now have these denominators. When we look at sine, cosine, and tangent, 1 and 1 are constants. So there's never going to be a problem there. There is going to be a problem with tangent when we have x in the denominator. And what I mean by we have problems is that it's possible on the unit circle for us to have values of 0 for either x or y. And where does that happen? Well, looking at cosecant, right, we would have issues if y was 0. Well, there's places on the unit circle where y equals 0. Right here at 1, 0, and over on the other side at -1, 0. So at both of these situations, right, if I said, what about what about this, right? The cosecant of 180 degrees. Well, that's talking about this point over here. And so I would write that out and I'd be like, okay, it's 1 over the y value. Uh-oh, that's undefined. And when we start to talk about trigonometric ratios as trigonometric functions, which is really what we're going for here, you'll learn that there's a discontinuity. There's a gap in the domain of cosecant at these values at 0 and pi, or 0 and 180 degrees. Same thing with secant, right? Secant of, if we did 90 degrees, or let's just say pi over 2, and I'll mix it up with some radians. Okay, secant of pi over 2, that would be up here, and that coordinate is 0, 1, and secant is 1 over x, so it would be 1 over 0 again. So we have problem there, and we will also have a problem at down there at 270 degrees, or 3 pi over 2. And then a cotangent, obviously, also whenever y is 0, it'll have these same issues that cosecant have, right? Wherever cosecant has a problem because y equals 0, cotangent will have that same problem. Okay, and notice also that is when sine is 0. That has a these cosecant and cotangent both have problems when sine is 0 because sine of theta is y.